Okay, I hope I'm audible to all students who are attending this lecture of mathematics. We intend to start with a very important and new topic within mathematics and statistics. This is called as the theory of probability. This is a very important and indeed a very interesting topic within mathematics and statistics. Okay, now let's first of all look at some of the important terminologies which we have within our topic on probability. Okay, so first of all, let us understand what is meant by an experiment. So an experiment is any activity. An experiment is any activity or process whose outcome is subject to uncertainty. So any activity or process whose outcome is uncertain is called an experiment. Whenever you are conducting an experiment, be it in the field of science or in the field of economics, okay, whenever you are conducting an experiment, you don't know the outcome for sure. Outcome is subject to uncertainty. Okay, so now let us understand what is meant by the sample space of an experiment. Okay, let's understand the concept of sample space. Okay, so the sample space of an experiment, the sample space of an experiment denoted by delta is the set of all the possible outcomes of that experiment. The sample space of an experiment denoted by delta is the set of all possible outcomes of that experiment. That means when I'm conducting an experiment, if I list the set of all the possible outcomes which can occur, that is going to give me the sample space of an experiment. Let's take very simple example, and the sample space I denote in my lectures by delta. So consider the example of tossing a coin. Consider the example of tossing a coin. Now it's an experiment. We don't know the outcome with certainty. What will be the sample space? So I can write the sample space. The sample space of this experiment is delta taking two values. Either it can take the value heads or it can take the value tails. Okay, so when you are tossing a coin, the sample space of this experiment has two outcomes. Either it can take the value heads or it can take the value tails. Okay, now consider the example. Consider the example of tossing two coins. Consider the example of tossing two coins simultaneously. Now, what will be the sample space of this experiment? If you're tossing two coins, either both can give you heads, or the first coin gives you heads, second coin gives you tails, or the first coin gives you tails, second coin gives you heads, or both the coins give you tails. So this is my sample space of the experiment. Similarly, if I change this to consider the example of tossing 3 coins. If I change this to 3 coins, now what will our sample space be? Suppose we are tossing 3 coins simultaneously. What are the outcomes we can have? Either all the coins can give me heads, or first 2 coins give me heads, last gives me tails, or I can have HTH, heads, tails, heads, or I can have tails, heads, heads, or I can have tails, heads, tails, or I can have tails, tails, heads, okay, or I can have heads, tails, tails, or I can have tails, tails, tails. So you can see how many possible outcomes I can have if I am tossing 3 coins simultaneously. I can have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Okay, so do you observe a pattern? Just for a very interesting fact, if you toss 1 coin, you have 2 outcomes. If you toss 2 coins, you have 4 outcomes. If you toss 3 coins, you have 8 outcomes. So I can write a note. In general, if we toss n coins, then the sample space will consist of how many outcomes? Then the sample space contains 2 to the power n outcomes. You can clearly see if you toss 1 coin, you have 2 to the power 1, that means 2 outcomes. If you toss 2 coins, you have 2 square, which is 4 outcomes. On the screen, you can see if I toss 3 coins, I have 2 to the power 3, which is 8 outcomes. So in general, if I toss n coins simultaneously, the sample space is going to contain 2 to the power n outcomes. Okay, so I hope all students have understood the concept of experiment. Any activity or process whose outcome you do not know with certainty. You have possibilities, but you don't know the outcome with certainty. That is called an experiment. Sample space of an experiment, which I denote by delta, is the set of all possible outcomes of that experiment. And we have understood this using an example. Now, what is meant by an event in probability? So let's quickly revise this. What is meant by the event? I can say an event is any subset. Now, students have learned the concept of subset in my lectures on set theory. An event is any subset of the outcomes contained in the sample space delta. An event is any subset of the outcomes contained in the sample space delta. So we have just done the concept of sample space. Sample space gives us the set of all possible outcomes of an experiment. Now, from the set of all possible outcomes, if I take a few outcomes, that gives me the event. So, for example, consider the experiment. Consider the same experiment of tossing 2 coins simultaneously. What is the sample space? Sample space is a set of all possible outcomes: heads, heads, head, tails, tail, heads, tail, tails. Consider the following events. Consider the following events, which are described as follows. Event is exactly 2 tails occur. and B is at least one tail occurs. Now, what will A be? Exactly two tails occur is only one event, PT. You can see that this is a subset of the sample space delta. The event A lies within the sample space delta. What is my event B if I write it in set form? At least one tail occurs. At least one tail occurs means exactly one tail occurs or two tails occur. Because when you're tossing two coins, at least one tail means either one tail or two tails. So again, you can see this is a subset of the sample space delta. So these are two events. Now event A consists of only one outcome. So I can say that event A is a simple event. Event A is a simple event as it contains only one outcome. On the other hand, event B is a compound event. Event B is a compound event as it contains more than one outcome. As it contains more than one outcome. So all students can clearly see this. When I talk about event A, it consists of only one outcome, tail tail. It's a simple event. So simple events are those events which consist of only one outcome. Event B, on the other hand, you can see consists of exactly three outcomes, or I can say more than one. So event B is a compound event as it consists of more than one outcome. Okay, so hoping students have understood the concept of experiment, sample space, and event. Okay, so now if we move forward, now in general, what is meant by probability? So now let us introduce the concept of probability. So probability of an event A is equal to set of all outcomes in A divided by set of all outcomes in the sample space, which I call as delta. So if I have to find the probability of an event A, it is equal to set of all outcomes in A divided by set of all outcomes in the sample space delta. Another way of saying it, probability of an event is the set of all favorable outcomes divided by total number of outcomes. Okay, so now our objective in this particular lecture is to study the concept of conditional probability. We look at the concept of conditional probability. Basic probability we have already learned in class 11 mathematics. Okay, in this particular lecture where we intend to look at probability at class 12th level, the objective is to now start with the first topic within the probability at class 12th level, which is conditional probability. Although we have done the basic concepts of probability in our lectures in class 11. Okay, so now let us focus on the definition of conditional probability. So if E and F are two events associated with the sample space, which I denote by delta, of a random experiment. If E and F are two events associated with the sample space delta of a random experiment, then the conditional probability of the event E, given that the event F has occurred, is given by probability of the event E, given that event F has already occurred, is equal to the probability of event E and F. Now, in probability and in set theory, and is denoted by intersection. Probability of E and F divided by probability of F. Provided probability of F, which is in the denominator, is not equal to 0. All students can note that in probability and set theory, intersection denotes and, union denotes or. We have done this in our lectures on set theory as well. So probability of the event E occurring, given that the event F has already occurred. So I can say conditional probability of E. This is nothing but the conditional probability of E, because it is conditional or dependent on the fact that event F has already occurred. Okay, so this is given by the formula probability of E intersection F divided by probability of F, provided probability of F is not equal to 0. Okay, now let us look at the concepts. Let's look at the properties of conditional probability. So our heading is properties of conditional probability. So let capital E and capital F be the events of a sample space delta of an experiment. Then we have the following properties. We have the following properties. Okay, so this is property number 1. Probability of the sample space delta, given the event F has occurred, is exactly equal to probability of the event F, given event F has occurred, is equal to 1. So this is the first property. Probability of the sample space given that the event F has occurred is equal to probability of the event F, given event F has occurred, is exactly equal to 1. Let's quickly look at the proof of this. Okay, so by definition, consider probability of the sample space given event F has occurred. By the definition of conditional probability, what is the formula? Probability of delta intersection F upon probability of F. Now, what is the intersection of the sample space with the event F? If I draw a Venn diagram, to explain this to all students. This whole is my sample space delta. Within that, I have an event F. Okay, so what is the intersection of delta with F? It is equal to F itself. What is the common part between delta and F? Now F is lying within delta. So the intersection of delta and F is nothing but F itself. So this is probability of delta intersection F is nothing but probability of F divided by probability of F, which is equal to 1. Similarly, consider probability of F given F. This will be by definition probability of F intersection F upon probability of F. From the basic set theory, we know what is the intersection of F with itself. Intersection of the event F with itself is nothing but F only upon probability of F, which is equal to 1. So I hope all students have understood the first property. Probability of sample space given that event F has occurred is equal to probability of the event F given that event F has occurred, which is equal to 1. Okay, let's now look at the second property, property 2. If capital A and capital B are any two events of a sample space delta and F is an event of delta such that probability of F is not equal to 0, then probability of A union B given that the event F has occurred is equal to probability of A given F has occurred plus probability of B given F has occurred minus the probability of A intersection B given F has occurred. Okay, so let's look at again, let's read the statement and then we can look at the proof. If capital A and capital B are any two events of a sample space delta, and F is another event of delta such that probability of F is not equal to 0, then probability of A union B given that the event F has occurred is equal to probability of A given F has occurred plus probability of B given F has occurred minus probability of A intersection B given that the event F has occurred. Okay, so now let's look at the proof of this particular statement. Okay, so the proof is as follows. Let's start with the definition of conditional probability. So consider probability of A union B given F. What is the basic definition, guys? This is going to be probability of A union B ka intersection with F divided by probability of F. This is by definition of conditional probability. This is by definition of conditional probability. Therefore, I can write probability of A union B given the event F is equal to, now I can apply the properties of distributive law which we have learned in set theory. Okay, this is probability of A intersection F union B intersection F upon probability of F. This is nothing but the distributive law. This is the distributive law of the union of sets done in class 11th mathematics. in class 11 mathematics, we had done the concept of set theory and we had done the distributive law of union of sets. So this is the distributive law we have applied. So now you can clearly see, if I move forward, what is the probability of A union B? If all of you can recall, probability of A union B is probability of A plus probability of B minus probability of A intersection B. Again, we have done this in our lectures on probability in class 11th mathematics. So if I apply it here, probability of this union, this will be probability of A intersection F plus probability of B intersection F minus probability of A intersection F intersection B intersection F upon probability of F. All students can recall that probability of A union B is probability of A plus probability of B minus probability of A intersection B, provided A and B are not disjoint events. Okay, so this was the formula which we had done in class 11th mathematics. So if I apply it here, probability of A intersection F union B intersection F will be probability of A intersection F plus probability of B intersection F minus probability of A intersection F intersection B intersection. Now if I erase the initial part and if I continue with the proof on the top, let us see what do we get. So if I continue with the proof on the top, I can write probability of A union B given F is equal to probability of A intersection F divided by probability of F. I'm separating the terms now, probability of B intersection F divided by probability of F minus probability of A intersection F intersection B intersection F. I can write probability of A intersection B intersection F divided by probability of F. I can write it like this because A intersection F and B intersection F ka intersection will be A intersection B intersection F. Okay, so if I now erase the remaining part and if I solve it further, let's see what do we get. So I can write therefore probability of A union B ka intersection with F is equal to, this term is nothing but by definition probability of A given F, probability of A conditional on F, plus this term by definition is nothing but probability of B conditional on the event F, minus this I can write as probability of A intersection B intersection F divided by probability of F using the associative law in set theory. This is the associative law which we had learned in set theory. And now you can see that we get the final answer. If I erase the bottom portion of the screen and write the final statement that proves our result. So therefore, probability of A union B intersection F is going to be probability of A conditional on F plus probability of B conditional on F minus this I can write as probability of A intersection B conditional on F by definition. So hence you can see that the statement is now proved. This is what we had to prove. So hoping students have understood this and have no doubts. Okay, now let us look at a very important sub case. Suppose A and B are disjoint events. Suppose A and B are disjoint events. So if I erase the initial part and if I write a no, if I erase the initial part, let me write a note. So if A and B are disjoint events. Now, when are two events said to be disjoint? All students can recall two events are said to be disjoint if they have nothing in common. Again, we have learned this in our lectures on set theory. If two events have nothing in common, they are said to be disjoint events. So if A and B are disjoint, it simply means that A intersection B is equal to the phi or the empty set, called the empty or the null set. It does not contain any element. A intersection B is equal to phi, so I can say therefore probability of A intersection B will be probability of A intersection B is equal to phi, and all of us know that probability of a null set or an empty set is equal to 0. So what will my statement now be? So I can say therefore probability of A union B given that the event F has occurred will be equal to, it will be equal to what? It will be equal to probability of A given F has occurred plus probability of B given F has occurred minus, what will this term be now? Now A intersection B is phi. So I can write probability of A intersection B is phi because A and B are disjoint. Phi given the event F has occurred. Now probability of phi given any event has occurred is equal to 0. So I can write therefore probability of A union B given that the event F has occurred is equal to probability of A given F plus probability of B given F. Since in the bracket I can write probability of phi given F is equal to 0. That simply means that if two events A and B are disjoint, they have nothing in common, their intersection is phi, then in that particular case, our result will be probability of A union B conditional on the event F occurring is equal to probability of A given F plus probability of B given F. Because probability of phi given F will now be equal to 0 if A and B are disjoint events. So hoping all students have understood this property. This was property 2 for all of us. Now, let's look at property 3. Let us look at property 3. Okay. So probability of E complement given that the event F has occurred is equal to 1 minus the probability of E given the event F has occurred. Now all of us should know the concept of complement. So if I draw a Venn diagram to quickly revise, if this is my sample space delta and this is my event E, then E complement will contain those elements which are in the sample space but not lying in E. That means all the area outside E is going to be my E complement. All the area which is outside E is E complement. So now we need to prove this result. Okay, so let's look at the proof. Now recall from property 1, which we have done. Property 1 was that probability of the sample space given the event F is what? We had shown that this is equal to 1 from property 1. All of you have written down property 1. Please check it. Probability of the sample space given the event F is equal to 1. So this implies, now what is delta? Now guys, from this diagram, you can see that delta is nothing but the union of E with E complement. If I take the union of the set E, this is my set E. If I take its union with E complement, it's going to be the whole area, which is nothing but my sample space delta. So I can write my delta is nothing but E union E complement conditional on F equal to 1. Since in the bracket I can write my sample space is nothing but E union E complement. And now what will this be? Now from property 2, all of you can recall that E and E complement are disjoint events. They have nothing in common. There is no intersection. E and E complement are disjoint events. They are not intersecting. Okay. If you look at E and E complement, if I draw the diagram again for all students, this is my whole sample space delta. This is my event E, and outside this is my event E complement. You can see that there is no intersection between them. And from property 2, we have just learned that if two events are disjoint events, then I can write this expression as probability of E conditional on F plus probability of E complement conditional on F equal to 1. We learn this from property 2. From property 2, since E and F are disjoint events. Therefore, I can write from this particular equation, I can write probability of E complement given F is 1 minus the probability of the event E given F. Hence, so hoping students have understood property 3. It was indeed a property which was using the results from property 1 also and from property 2 also. From property 1, we had learned that probability of the sample space given the event F is equal to 1. From the Venn diagram, you can see that sample space I can write as E union E complement. So probability of E union E complement given F is equal to 1. This I can further write like this. Probability of E conditional on F plus probability of E complement conditional on F equal to 1. From property 2, we can write this since E and F are disjoint events. And this I can further write like this. Probability of E complement given F is equal to 1 minus the probability of E conditional on F. So hence this result is true. Okay, so now let us look at some practice questions based on the concepts which we have done. Question 1. Practice questions I can write based on conditional probability. Let's look at the practice questions based on the concept of conditional probability. So if probability of A is given to us as 7 by 13, probability of B is given to us as 9 by 13, and probability of A intersection B is given to us as 4 by 13. All of us know that probability of any event should lie between 0 and 1. We know this from the basic probability we have done in class 11. Okay, so the question asks us find probability of A conditional on B. So let's look at the formula. Conditional probability of A given that event B has occurred is probability of A intersection B divided by probability of the event B. Now A intersection B probability is 4 by 13 divided by probability of B is 9 by 13. 13 cancel. Our answer is 4 by 9. So conditional probability of event A given that event B has already occurred is equal to 4 by 9. Okay, and let's look at the last question for this lecture, after which we stop. Okay, a family has 2 children. What is the probability? What is the probability that both the children are boys, given that at least one of them is a boy? Okay, a family has 2 children. We need to find the probability that both the children are boys, given that at least one of them is a boy. So first of all, let us describe the sample space. Okay, so let B denote a boy and let G denote a girl. So describe the sample space of this experiment as, describe the sample space of this experiment as, what is my sample space? There are 2 children. So either both of them can be boys, or first one is a boy, second one is a girl, or first one is a girl, second one is a boy, or both of them are girls. These are the set of all possible outcomes we can have for a couple who is having 2 children. Now, let the event A denote both children are boys and let the event B denote at least one of them is a boy. What do we need to find out? We need to find out what is the probability that both children are boys, given that at least one of them is a boy. So we need to find the probability that both children are boys, which is A, given at least one of them is a boy, which is B. So we need to find out probability of A given B. This will be probability of A intersection B divided by probability of B by definition. Now, what is probability of B? What is the probability that at least one of them is a boy? Now, at least one of them is a boy means either both boys or one boy. So total number of outcomes is how much? Total number of outcomes is 4. And favorable number of outcomes is 3. So I can write what are the total outcomes in the sample space? Total outcomes in the sample space delta is 4. And favorable number of outcomes means at least one of them should be a boy. That means where can we find at least one boy? 2 boys, 1 boy, 1 boy. So 3 outcomes. So probability of B is 3 by 4. Now what will probability of A intersection B be? Probability of A intersection B will be read as probability of A and B. So what is the probability that both children are boys and at least one of them is a boy? If I combine both of them, it boils down to probability that both children are boys. If I have to find the probability that both children are boys and at least one of them is a boy, together their intersection is going to give us both children as boys. So probability of A intersection B will again be, what are the total number of outcomes? 4. Favorable number of outcomes? Only 1. So probability of A intersection B is 1 upon 4. Because if you see, probability of both children boys and at least one of them is a boy comes down as probability of both children being boys. And both boys is only one possibility out of the 4 possible possibilities. So now I have got probability of B. I have got probability of A intersection B. I have to find out probability of A given B. Apply the formula. Probability of A intersection B is 1 upon 4 divided by probability of B is 3 upon 4. 4 and 4 cancel out. My required answer is 1 upon 3. So probability that both the children are boys, given that at least one of them is a boy, is equal to 1 upon 3. So students, this is where I intend to stop in this particular lecture. The objective of this lecture was to introduce the basic terminologies of probability, which we have done in class 11th mathematics, and to introduce the first concept of probability within class 12th mathematics, which was the concept of conditional probability. The basic probability we have all covered in class 11th mathematics. The objective was to introduce the basic terms like experiment, sample space, event, and then directly start with the first major concept in class 12 probability, which is conditional probability. We have done the definition, properties, and 2 practice questions in this lecture. In the next lecture, I shall be continuing with more practice questions based on the concept of conditional probability. So I stop in this lecture. Any doubt, you can unmute your mics and ask, or you can call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.